Section 2.3 covers the chemistry of water, and we're going to build on what we learned in the last lecture about the polarity of the water molecule and the hydrogen bonding that occurs between the molecules, and look at the chemistry of the water a little bit more. So according to your textbook, the first cells evolved in water, and we know that all living things are 70 to 90% water. The Earth, in fact, is 75% water. We learned in the last lecture that water is a very polar molecule, and because it's polar, it hydrogen bonds to each other, to other water molecules, and this allows our Earth to be covered in water and it to be liquid on the surface of the Earth due to this hydrogen bonding. Water also has a very high heat capacity, and remember by definition that a calorie is the amount of heat energy needed to raise the temperature of 1 gram of water 1 degree Celsius. And the hydrogen bonds that hold the water molecules together absorb heat, and that causes the water to be able to absorb the heat and not really change in temperature right off. And this allows organisms to be able to maintain their internal body temperatures, because the temperature of water will rise and fall slowly as well, and this helps us to be protected from rapid changes in temperature. So if it's very hot outside or very cold outside, we can go outside without fear of freezing or boiling away the water that we have in us. Water also has a very high heat of vaporization, and if you remember from chemistry, the heat of vaporization is the amount of energy it takes to take a liquid substance to a gaseous substance. And with water, 1 gram will require 540 calories of heat energy to take it from water at 100 degrees to vapor at 100 degrees, and that's quite high. The high heat of vaporization is what gives animals in a hot environment an easy way and efficient way to release excess body heat as well. And it moderates the temperatures along the coast when you look into the physical science aspect of the properties of water. We also know that water is a solvent. It's the universal solvent, and due to its polarity, it will absorb and surround lots of living things, whether they're inside or outside living systems. Remember that like dissolves like, so water's polar, so it will dissolve other polar substances, and most substances we have are polar substances when we talk about the substances we deal with on a daily basis. Hydrophobic and hydrophilic molecules need to be addressed. So hydro meaning water, philic is love, phobic is fear. Hydrophilic molecules are attracted to water, and hydrophobic molecules are not attracted to water. If you look at this picture showing sodium chloride ion dissolved in water, and this is what's going on the molecular level. The sodium ion transferred an electron to the chloride ion, and this becomes positive, and it's going to be attracted to the negative side of the water molecules. So on the other hand, we have the chloride ion with a negative charge, and it's going to be attracted to the positive side of the water molecules. So this is what would happen when it dissolves in water. Water molecules are both cohesive and adhesive. Cohesion is the property that they have because they are attracted to each other due to the hydrogen bonding. Adhesion is the property that they have due to the fact that they are attracted to other polar surfaces, so they adhere. So if you can remember, adhesion is like a band-aid on your skin, so it adheres to other surfaces. Cohesion is where it adheres to itself. This allows water to be a great transport system, whether you're talking about inside living organisms or outside living organisms, because of these properties. And those properties, again, are due to the fact that water is so polar and it hydrogen bonds to itself. It also has a very high surface tension because of this hydrogen bonding. And the forces between the molecules are so great that the surface tension is great. And this is a picture of a water spider or a strider, and you'll notice that it doesn't have enough mass to break the surface tension of the water that it's on. Another property of water is the fact that as it freezes, it becomes less dense in ice form than liquid water. And this is something that we all have practical knowledge of, because you know when you have ice cubes and you put them inside of a glass and you pour a liquid on top of it, eventually the ice cubes are going to come to the top. They're not going to stay at the bottom because they are less dense than the liquid water that they're in. So as water cools, the molecules actually move closer together, and this causes water to expand as it freezes and causes ice to float. And this is a good thing for bodies of water because ice will form on the top that actually acts as an insulator. It doesn't freeze all the way through, so living organisms in a pond can stay alive even when the top's frozen. Here's a picture showing what water molecules would look like if they were in a drop of water, and you notice there's no rigid structure or pattern. They're just floating around, being attracted to the other molecules around them with hydrogen bonding. In this picture over here, we see that they've slowed down, that the kinetic energy isn't as high, so it's in ice form, and it forms a lattice because they're slowed down and they're closer to each other, and that forces them to go to a pattern that's going to allow the hydrogen bonding to occur, because that hydrogen bonding is not going to be overcome in solid form. And that lattice structure in the ice allows that to float because it's less dense than liquid water is, and actually expands when it freezes. Let's take a look at acids and bases. It also has a connection to water because when water ionizes or breaks into its ions, it forms hydrogen ions and hydroxide ions in equal amounts. Remember that acidic solutions are very high in H+ concentration or hydrogen ion concentration, and acids by definition are substances that release hydrogen ions when they dissociate in water. And an example of that would be hydrochloric acid. So when I put hydrochloric acid in water, it's going to dissociate to hydrogen ions and chloride ions. On the other hand, bases have a low hydrogen ion concentration, and if they have a lower hydrogen ion concentration, they must have a higher hydroxide ion concentration. An example of this would be sodium hydroxide. And sodium hydroxide, when it's put in water and dissociates, the sodium ion will be separated from the hydroxide ion. So by definition, our bases are going to have hydroxide in them. We measure the amount of hydrogen ion concentration by using a pH scale. And the pH scale usually ranges from 0 to 14, where 0 is very acidic, 14 is very basic, 7 is neutral. So a pH below 7 is acidic, which means that the hydrogen ion concentration in that solution is greater than the hydroxide ion concentration. If a pH is above 7, it's considered alkaline or basic. That means the same thing. And that means that the hydroxide ion concentration is greater than the hydrogen ion concentration. And at a pH of 7, we have equal amounts of hydrogen and hydroxide ion concentrations. This is just a good picture of some basic substances and where they would fall on the pH scale, going from hydrochloric acid over here with a very high H+ ion concentration and a very low hydroxide ion concentration, all the way around to where, if you'll notice, as the blue increases, that's the hydroxide ion concentration increasing. As it increases, the hydrogen ion concentration decreases. So over here with sodium hydroxide and oven cleaner, these have a higher hydroxide than hydrogen ion concentration, and they're very basic. Buffer systems occur in living organisms, and a buffer is a chemical or combination of chemicals that keep the pH range within normal limits. And a good example of this is the bicarbonate ions and the carbonic acid that's found in our blood. And our blood normally needs to be at about a 7.4 pH, and if it varies at all, you could die. So these buffering systems within our blood help to keep an increase in hydrogen ions or an increase in hydroxide ions in our blood system within a normal limit so that it doesn't affect our overall well-being. And that concludes our discussion over the properties of water and acids and bases.